Right, this week we're going to talk about a physics concept called momentum. You've probably heard of this term before, and maybe have even kind of an idea of what it's about. The momentum is actually given by the letter P. M is already taken by mass. P actually comes from like impetus, though, so it's like P for it's a Latin word. It starts with P. I don't remember what it is. But anyway, P is going to represent momentum for us in this week's physics problems. And you can, if something is pretty massive, you might say it has a lot of momentum. But you also might say something has a lot of momentum if it's moving very fast. And the reason for that is because the equation of momentum is pretty simple. It's the mass of an object times its velocity, mv. That's it. So that's going to be a pretty easy week, I think, of physics. M times v, mass times velocity, is how you calculate the momentum of an object. And so it could be going at a constant velocity and not accelerating. So there's no force being acted upon it, but it's going at constant velocity. Then it still has momentum. So you can have momentum without having a force being applied. That's what Newton said. So as always, we need to discuss a couple things about this equation. First of all, what are the units? What are the units for momentum? The MKS units, and we can plug in the MKS units for mass and velocity, and the MKS units for mass is kilograms, and the MKS units for velocity is meters over second. So the units for momentum that you're going to be using are kgm per s. And there is, normally we take the MKS units and we say, okay, what's the derived unit that we're going to use that make this better, so it's not so ugly of a unit? There is none for momentum. Momentum is just remains kind of ugly units. kgm per s. That's what you're going to use for your units. Okay, the other question we usually ask about these things is momentum a scalar or a vector quantity? Is it a scalar or a vector quantity? We always hope it's a scalar quantity, because if it's a vector quantity, of course, that means we're going to have to do vector problems again. So mass, is a scalar quantity, right? It has no direct, you don't say 3 kilograms west or something. It just has a magnitude. Velocity, though, we know is a vector. Velocity is a vector. You need to tell me the magnitude and you tell me the direction it's going. And so when you take a vector times a scalar quantity, of course, you do have a vector quantity. Momentum is a vector quantity, and therefore we're going to do a lot more vector problems this week in this unit on momentum. Okay. I'm going to rewrite this equation a little bit because we could talk about changing our momentum. This was just the way I wrote it up here was just constant momentum. But we can change our momentum. And how would we change our momentum? Well, you could change your mass, but generally if you're just running along or something, that's not how you're going to change your momentum. You take your mass times a change in velocity. We need to change our velocity so that we can change our momentum. Now that you know something a little bit about, changing your velocity is called an acceleration. It's called an acceleration. And if it's an acceleration, that means we need to apply a force. So if you're going to change your momentum, you do need to have a force happening. So we can derive a kind of a new equation. We can go back, since we need force and we need to accelerate, we can go back to Newton's second law, our famous and favorite Newton's second law, F equals ma. And I'm just going to plug in some things here that you could easily do and understand. F equals m. What is acceleration? Acceleration is a change in velocity over a change in time. Right? A change in velocity over change in time. That's pretty easy to do. If I take the change in time times the other side over here, I would get force times a change in time equals mass times a change in velocity. And if you look at that right there, you see that that is change in momentum. That's the same thing as change in momentum. So we just derived an equation. The change in momentum would equal a force times a change in time. Basically a force times how much time you apply that force. How much time you apply that force. So this equation is how we change our momentum. So here's your basic, our basic equation for momentum is mass times velocity. We're going to use that a lot. That's really easy. But another equation that we're going to kind of look at is force times time. I'm going to rewrite that. Force times change in time equals mass times change in velocity. And this right side, of course, is change in momentum. This formula here, which we're also going to be using, we'll do a couple example problems, is called an impulse momentum equation, the impulse momentum theorem. So the left side, the force times the time, is called an impulse. So you apply a force for a certain amount of time to an object, that's called giving it an impulse. And the way you calculate the impulse is take force times time. It's very easy, force times time. If you do that, if you apply an impulse to it, then the object's momentum will change. And so m times change in velocity is the change in momentum. So impulse momentum theorem. The left side is impulse and the right side is change in momentum. And of course the units are the same on these. If you take a force, that's a mass times acceleration, that's a kilogram meter per second squared. My pen is not writing anymore for some reason. Kilogram meters. Sorry about that. Let's see. Kilogram meter per second squared is a force times another second. That would cancel a second out, right? And you'd have a kilogram meter per second. That would be the units for impulse, which of course is the same units for momentum. So the units on either side of this equation, this impulse momentum theorem, are the same. And we're going to do at least one problem here, an example problem of applying this impulse momentum theorem. And then we'll eventually go back to doing a lot of stuff with this equation. But these are basically your two main equations that we're going to have in this unit. So let's analyze this right here. And if you have your books, we're going to do the checkmark 5.14 problem. It's an impulse momentum type of problem. So here's the problem. It says a 0.15 kilogram baseball leaves a bat with a velocity of 120 miles per hour. The ball was hit with a force of 7,041 newtons and was in contact with the bat for 0.0020 seconds. How fast was the ball pitched? Thought this was a good problem to do since we're all wanting to get out and watch or play some baseball right now. This would be a good problem to maybe analyze. We can at least do baseball in our brain with physics. Fun, right? Okay. One of the problems right here is the velocities are not in the correct units. So I'm going to give you a conversion factor here. If you remember, 1 mile per hour equals 0.447 meters per second. So I can take that 120 miles per hour and I can multiply by 0.447 if you do your dimensional analysis correctly. And this velocity is actually like 53.64 meters per second. So we'll use this as our velocity. Okay, so we're going to use the impulse momentum theorem here because we have a force that we're applying it to. We have a mass that we're applying the force to. We have an initial velocity right here, and the ball's in contact with the bat for a certain time. So we have time, we have mass, we have our force, we have an initial velocity. So that has about everything we need. So force times a change in time equals mass times a change in velocity. I can write this as force times time, since our starting time is 0. The delta t could just be whatever our time is. Force times time equals mass times change in velocity would be Vf minus Vi. That's a change in velocity. We're trying to figure out how the final velocity. How fast is the ball going to be leaving the bat? So we're going to take a force times time. We're going to divide by the mass. And then we're going to add the initial velocity, and that should equal our final velocity. And we're going to have to actually put it back into, we'll go ahead and put it back into miles per hour at the end. Okay, so the final velocity then should equal the force, which is 7,041, times the time that it's in contact with the bat, which is 0.002 seconds. We're going to divide that by the mass, which is 0.15. Looks like we're going to need 2 sig figs in our problem here eventually. Plus our initial velocity, which was 53.64. Don't use the 120, remember. Okay, and that should give us a final velocity. So I'm going to put that in the calculator real quick. 7,041 times 0.002 divided by 0.15 plus 53.64. And I get 147.52 meters per second. And if I want to convert that, it's 0.447 meters per second for 1 mile per hour. So I'm going to divide this by 0.447, and I get a, I got something completely wrong here. Let's see. What did we do? Force times mass, divided by mass. We're going to add the velocity. Did I get that original one right? Let's see. 7,041 times 0.002 equals, divided by 0.15, that's in kilograms, that's right, plus 53.64 equals, and I do get 147.52 meters per second, divide by 0.447, and I get a velocity. Oh, I see what I did wrong. I'm not going to remake this video. I'm just going to show you. You're going to all have to wait. And maybe you've been screaming at me the whole time. This 120 miles per hour is how fast the ball leaves the bat. So this is a final velocity. Oh, silly. Final velocity, okay? How fast was the ball pitched? That's the initial velocity. That's how fast it's coming in. All right, so what are we going to do here? We're going to divide by the mass. We're going to, okay, so we're going to come back in here in this problem here. I'm going to come down here. I'm going to erase right here this step right here. Oh, I should have practiced this ahead of time. Okay, so we're going to F times T divided by M, and that will equal VF minus VI. We want to solve for the VI. So we're going to take the VI to the other side, add it on over the other side, and then we have VF minus FT over M. That's what we're going to do instead. Okay, so we'll go ahead and erase this other stuff here. Okay. Don't tell your friends to speed up to the end. Make them suffer through this video also. All right. So VI should equal VF, which is 53.64, minus the force, 7,041, times the time, which is 0.002, divided by the mass, which is 0.15. Let's try this. 53.64 minus 7,041 times 0.002 divided by 0.15 equals, and I get a negative 40.24. That is in meters per second. I'm going to do 1 mile per hour is 0.447 meters per second divided by 0.447. That is a negative 90 miles per hour. Wow, that took forever. Okay, why negative? Why negative? Well, remember, velocities are vectors, right? And our final velocity was a plus 120. So, our final velocity, the ball is going out this way. plus, we'll say 120, we'll say it was to the left. Okay, that means the initial velocity was coming in this way. The ball was being pitched in this way. That has to be opposite whatever this was. So since we designate this as plus, going out into the field, the pitch has to come in at a negative 90 miles per hour, which makes sense. That's something that some major league pitchers can pitch. Okay, so negative 90 miles per hour would be our incoming velocity, and 120 miles per hour would be the outgoing velocity. So if you have your books, we're going to look at 5.15, and it looks like a pretty simple question. It says, what is the angular momentum of the Earth? Angular momentum. So, as always, remember, when we introduce an equation, we also can talk about what happens if it's not moving from one location to the next, but it's actually just rotating. And we can rewrite the equation with the correct symbols for that. So, if you remember, momentum is mass times velocity. So what is angular momentum in rotational world? Well, what do we put in for mass? Well, remember, if you're rotating something, it's not just dependent on the mass, but it's also dependent on how that mass is distributed throughout the rotational item. So instead of m, we use something called rotational inertia, capital I, and there's an equation for that, depending on what the object is. What's the velocity? Well, it's going to be angular, not linear velocity, v. It's going to be angular velocity, which is but, or omega. Okay, so here's another equation, I guess. I guess we had introduced 3 equations today. Sorry, I lied. Momentum is I but. Okay, that's angular momentum. And this question here is saying, what is the angular momentum of the Earth? So it looks pretty easy. There's only 2 parts to it. So momentum would be I. So what is I of the Earth? What is the rotational inertia of... There's something on my iPad there that I can't write with. Yeah, what is the rotational inertia of the Earth? And the Earth is a ball, right? It's a ball. Okay? So the equation for that is 2/5 mr squared. 2/5 mr squared. What is the angular velocity of the Earth? We talked about this, I think, before we went on break. What is the angular velocity of the Earth? We all do know what it is, right? It's pretty easy. How many times during the day does the Earth turn around? And we know that the rotational velocity of the Earth is once per day, right? Once per day. Okay, so we have to maybe do some dimensional analysis there. Once per day, 1 day is 24 hours, right? And 1 hour is 3,600 seconds. We didn't quite finish that. We just did the times, right? So now we have revolutions per second. 1 revolution is how many radians? Correct. Very good. 2 pi, right? 2 pi. So now I can cross off that. Now I'm in radians per second. Okay. So your angular momentum is 2/5 times the mass. What's the mass of the Earth? It's 6e24 kilograms, if you remember that. Times the radius squared. What's the radius squared? 6.37 e6 is the radius in meters, right? And you square that. Okay. And then it looks like you're going to take that times 2 pi. And then it looks like you're going to divide all that by, you can divide this by a 24 and a 3,600, right? And of course you have a 5 down here also. Okay, so I'll try to put that all into the equipment. Maybe I'll do it for you. 2 times 6e24 times 6.37e6 squared times 2 times pi divide by 5 divide by 24 divide by 3,600. No idea if this is right. I believe it's right. I'm just going to write it down and you're going to check and see if you get the right thing. So 7.1 E 33. 7.1 E33 is the angular momentum for the Earth. The angular momentum for the Earth. I'm going to let you figure out what the units are. You have to plug in the units kind of in for some of these things in here. The angular momentum units aren't actually the same as kgm over s. So I'll let you figure this out. Put in the units and see what the angular units for momentum actually are. I think that is enough. That's over 20 minutes lecture. So that's our first introductory lecture on momentum. And then in the next couple of lectures, we're going to get into the really the big stuff with all the big math on the conservation of momentum.